Well, hello there, good people. Today we are going to be, whoa, okay, we got stuff happening. Today we are going to be talking about thermal processes. Now, if you look here, I have a question for you. It says, a cylinder with a movable frictionless piston contains an ideal gas that is initially in state 1 at 1 times 10 to the 5th pascals, 373 Kelvin, and 0.25 meters cubed. The gas is taken through a reversible thermodynamic cycle as shown in the PV diagram above. We're going to focus on these last two parts of the questions. Can you calculate the net work done on the gas during the cycle, and was heat added to or removed from the gas during the cycle? By the end of class today, or by the end of this video, the hope would be that you would actually be able to do this kind of question. Though at this point, you probably say, I have no idea what this thing is even talking about. Today, we are talking about thermal processes. And this is a slideshow built to expand your view of the world, engage your mind and work, and turn up the heat on some old energetic concepts. Now, before we can even talk about thermal processes, there are actually a few other things that we need to talk about. Mostly, we need to review some things that we talked about last time. The last time that we talked, we were learning about the four laws of thermodynamics, and we learned that I'll go orange here. Orange, can you even see orange, or is that going to be way too much? Let's go, I like the blue because it's like the less aggressive. It's the least aggressive in neon to me, but we'll go purple. Okay, so we learned that the first law of thermodynamics says that your change in internal energy is equal to work plus heat. Meaning, if you add work to something, then you can change its internal energy. If you add heat to something, then you can change its internal energy, and the total internal energy is going to be changed by however much work or heat is added or taken away. Now, this equation you'll remember from last time. Oh, and I forgot, I don't have it on do button. This equation you'll remember from last time. And now what we're going to be doing here in these thermal processes is all of these are going to have to do with gases. So in all of these, we are either going to be applying work to a gas or putting heat into a gas and seeing what happens to the internal energy of the gas. So for all of these thermal processes, we're seeing how each of them apply to gases specifically. Now, when we look at these, we actually have a special way that we can talk about work for a gas. For a gas, work, well, we know for anything actually, work is equal to force times distance. That's our generic equation for work. But then, for a gas, do you agree this is a fine algebraic move? I could literally just divide this by A and multiply this by A. Isn't that totally fine? Which would give me that work is equal to force over area. That's pressure. Change in length times an area. That's a change in volume. So we get an equation for work for a gas that says that work for a gas, or I mean really anything, but for this specifically because we have gases that are compressible. For a gas, work is equal to pressure times a change in volume. Now, this is very useful to us because when you're doing work on a gas, most of the time, do you see if I'm squishing it, I am applying a force for distance, but I'm also applying a pressure that is causing that gas to change its volume. So I say that work is pressure times a change in volume, and this equation applies to a gas. Now, we have to be very careful here because there's a little bit of a sign issue. Watch here. If I apply pressure, do you see that I just did work on the gas? We say doing work on the gas is called positive work because I just added energy into the gas. So I just did positive work. But do you see that the volume of the gas just decreased? So when delta V here is negative, when the volume decreases, we call that positive work. But when delta V is positive, when the gas expands, well, when the gas expands, it pushes outside on its environment, and pushing outside on its environment, it does work on its environment. So when the gas expands, it actually does, we have negative work because the gas is giving energy to its environment. When the gas contracts, work is being done on the gas. So a negative change in volume, the gas contracting, a negative change in volume ends up being positive work. And a gas expanding, a positive change in volume, is negative work. So in order to fix this issue here, we have a little negative sign in front of this equation. This equation says that work is equal to the pressure applied to a gas times the change in volume of that gas with a little negative sign in the front, meaning that if it gets smaller, we have positive work. If a gas gets bigger, we have negative work, as gas does work on its environment. Now, the last little thing that we'll see here is that we can use this on a graph. Here I have a pressure versus volume graph. Here's my volume in meters cubed. Here's my pressure in newtons per meter squared, like that. Let's say that I had a line here like this, Well, if I asked you to find the area under this graph, you would say, no problem. I'm just going to make it into a little rectangle. And then you'd say, there's my area. Then you'd say, well, to find the area, I'm just going to do base times height. You'd say the base of this thing, well, if this is my final volume and this is my initial volume, and then between here and here I have a little delta volume, you would say, well, my base is a delta volume. My height here is my pressure. So you would say the area under this graph is base times height, or pressure times a change in volume. This means that the area under a pressure versus volume graph is work. Work is the area under a pressure versus volume graph. Now, you can find the amount of work done by looking at a pressure versus volume graph and calculating the area underneath the graph. You can do that to find the amount of work. But if you want to know if that work was added to or taken away from the gas, you have to look at what the gas did. In this case, do you see that we went from an initial smaller volume to a final bigger volume, which means that this gas expanded. If the gas expanded, that's going to be negative work, because the gas was doing work on its environment, so it was giving up some of its energy to the environment. If the gas started like this, instead of having a V final here and a V initial here, if we change this guy and this was a V final and this was a V initial, so I started at a bigger volume and I ended at a smaller volume, if my volume decreased like that, and this graph was going this way, if the volume decreased, then I would say that the amount of work that was done on this gas was positive, because the gas was compressing and it was gaining energy as someone was putting energy into it. So you can look at the graph to find the work. You have to look at the change in volume to find the sign for the work. And then that's how we can calculate the work done on a gas. We will use this equation in conjunction with this equation a lot for the rest of the slideshow. Let's go ahead and take a look at what happens next. Let's clear this out, and I'm going to pause really quick. Okay, the first type of process that we're going to look at today is what we call an isobaric thermal process. For each thermal process, this is our first thermal process here. Here's our first one. For each of these processes, we're going to be looking at this equation, which says, whoa, I can write in the black part. That's crazy. I didn't even know that was allowed. Wow, watch this. Woo. Okay. For each of these thermal processes, what we're going to do is we're going to add heat to a gas, or do work on a gas, or add heat and then let the gas do work, or add work and then let the gas change the heat of something. So we're going to be adding like one of these in each of these four kinds of processes. So in the first one, we'll add heat and let the gas do work. In the second one, we'll add heat and not let the gas do work. In the third one, we'll add work and then we'll not let the gas give out heat. Then in the last one, we'll add work and then let the gas give out heat. So in each of these, we're just playing with these Q's and W's as we add heat or add work to a gas in each of the following scenarios. The first scenario is an isobaric thermal process. You know from word within the word that iso means same, baric means of pressure. So this is a thermal process that occurs at a constant pressure. Oh, there's the bell. A thermal process that occurs at a constant pressure. In other words, the pressure is not changing. Here's what this looks like. The way that this goes is you start by adding in heat. I like to do heat in red. You start by adding in heat. So we put heat in. After you put heat in, then this makes all of the particles start to move a whole lot faster, and they're hitting on the walls of the container. As they hit on the walls of the container, they're going to cause this thing to expand. And so, we add heat, we get some thermal expansion, and so your volume increases substantially due to thermal expansion. Due to thermal expansion. Yeah. When the volume of the gas expands, well, now the gas is doing work on its environment. So now the gas does work on the environment, which we say is a negative W, because the gas is doing work on its environment. If we were to write a delta U statement for an isobaric process, what we would say is that delta U is equal to adding heat in, and then the gas does work. Here's kind of what this looks like. This looks like, this is, by the way, the basis of most steam engines, which I don't have a steam engine that I can show you in a good format on a video like this. But here's the basis of most steam engines. What happens is you take a gas like this and you heat it up, heat it up, heat it up, heat it up, heat it up. When you heat it up, this thing expands because it has so much heat. When it has so much heat, it expands and it pushes up on a little piston. Notice, I put energy in, then it expands. When it expands, it pushes up on the piston and it does work on the piston. So I put in that energy, but then the gas puts the energy right back out again. This means that the total change in energy of the gas is 0 because I put heat energy in and then it released it back to the environment in the form of work. Then I put in heat, it gives that energy to the environment in the form of work. I put in heat, it gives that energy to the environment in the form of work. So that's what happens in an isobaric process. Now, in this kind of process, the reason why it's called isobaric, same pressure, is because if I had this guy here and I added heat and made all those molecules start moving faster, but I didn't let it expand, like this, if I held it on nice and tight and didn't let it expand, well then the pressure in there would get really, really big as all the little molecules are starting to move around really, really fast and they're hitting on the walls of their container really, really hard. But if I let it expand, well then the pressure isn't all contained. The pressure gets to push out on the walls, and so because it gets to push out on the walls, then the gas expands, and when the gas expands, it gets to stay at the same pressure. So this is a thermal process that occurs at a constant pressure. You put heat in, the gas spits it back out again into the world as work, and the total internal pressure of the total internal energy of the gas stays the same. In other words, we say that that gas doesn't hold on to that energy for any amount of time. It never gets to have it to itself. You put the energy in, it spits it back out. It's not actually changing its energy, kind of like if you had like a bathtub and you had the faucet on with the drain open. Is the bathtub filling up with water? Is it gaining water? No, because the water's flowing in and back out. Same thing here. The gas isn't gaining any energy because it's letting the energy flow into it and right back out again. This is an isobaric thermal process. Let me get cleared out here and then we'll go to the next slide. Okay, this is a graph of an isobaric process. In an isobaric process, you can see the pressure remains the same. This one shows the volume increasing. So if the volume is increasing, then the gas is doing work on its environment. Here you can see that as the pressure stays the same, the volume increases. The area under this graph here, that's the amount of work that gets done. Now, in order to determine whether this work is positive or negative, I look at how the volume starts small and gets bigger. I say that must mean negative work because the gas is doing work on its environment. And that is an isobaric process. Let's take a look next at our next type of process. Oh gosh. Oh, this is why I pause things. One sec. Okay, next we have an isovolumetric or an isochoric process. Both of these words mean the same thing. It means a process that is happening at a constant volume. Let's check our formula again. You'll remember delta U is equal to Q plus W. An isovolumetric or an isochoric process is a thermal process that occurs at a constant volume. The volume stays the same. Now, it's going to start out very, very similarly to an isobaric process. What you're going to do is you start by adding heat to a gas. Say that I add a bunch of heat to this gas, but then instead of letting it expand, suppose that I held my hand, let's make this a little bit bigger. Suppose that I held my hand on top of this guy like this so that I didn't let it expand. So I add heat, but I don't let it go where it wants to go. Well, I add heat, but I do not let the gas expand. In other words, I do not let V increase. No, I do not let the volume increase. This means that the gas does not get to do work on its environment. In other words, I add heat, I hold it still, and I don't let it expand, so the gas does not get to expand and push its energy outward into its environment. In other words, the amount of work that the gas does is, let's not save, is 0, like this. Here's what this would look like as a delta U statement. As a delta U statement, we would say that I add in heat, but I don't let the gas do any work. This means that the change in internal energy of the gas is going to be the amount of heat that I add. This gas is going to get more and more and more energy as I just hold this volume still. As I throw in a bunch of heat into this thing, well, those particles are moving faster and faster and faster. Their kinetic energy is increasing, and they try to thermally expand, but this is an isovolumetric process, meaning I force it to stay at the same volume. As I force it to stay at the same volume, the pressure is going to increase. Pressure is going to get nice and high because all of those little gases all those little gas molecules are all running into the walls, and they're hitting the walls so hard, but they can't go anywhere. So the pressure increases as they run into the walls harder and harder and harder. Pressure increases, and they have way more energy now because they're not allowed to dump that energy out into the environment. I'm putting heat energy in, but I'm not letting it go anywhere. So the gas just builds up and builds up and builds up energy on the inside. The amount of energy that it gains is equal to the amount of heat that I put in. Here is what an isovolumetric process looks like. An isovolumetric process on a graph. Here we go. Isovolumetric or isochoric. You do need to be familiar with both terms. An isovolumetric process or an isochoric process looks like this. Notice the volume stays the same, but the pressure increases as all of those little guys, all those little molecules don't get to go anywhere, so they're just running into the walls a little bit harder. As this happens, as this pressure is increasing, you'll notice the amount of work is the area under the curve. Well, do you see how there's no area under a straight vertical line? You can't make an area. You could try to find the area here. We would have to do base times height. There's a height, but there's no base. And so there is no area here, which feels good to us because we say that this gas does no work. So the fact that there is no area and the gas does no work, we say, yep, that looks pretty right to us in an isovolumetric process. The gas isn't allowed to expand, so it's not allowed to do any work. Those are the first two types of processes. Before we move on, check your notes, check yourself, and say, okay, wait a second, what's the difference between an isovolumetric and an isobaric process? What are the similarities? In both, we add heat, but in an isobaric process, we allow it to expand, meaning the gas takes that heat and applies it and does work on its environment. In an isothermal process, jumping the gun here. In an isovolumetric process, we add heat, but we don't let it expand, so it just stores up all that extra energy deep down inside of itself instead of releasing it to the environment and doing work on its environment. Okay, next we'll talk about an adiabatic process. Once again, let me write my equation here. An adiabatic process is a thermal process that occurs without heat transfer. It's a thermal process that occurs without heat transfer. Now, in our last two processes, what we've done is we have added heat and then either let the gas do work or not let the gas do work. In an adiabatic process, we are going to add work and then we'll see what happens with the heat. In an adiabatic process, we start by adding work to a gas. We start by adding work. Let me show you what this looks like. I gotta grab my little thing here. Okay, in an adiabatic process, I start by adding in work. Let me see if I can see it if I go like this. Okay, yeah, that's helpful. That's probably our best move. Okay, in an adiabatic process, I start by doing work on the gas. The way that I do work on the gas, I got all this stuff in the way here. The way that I do work on a gas is I squish the gas. Now, here's what I have. Here is I have this is a little canister of gas here. I can move this little doohickey this way to squish the gas, or I can move it this way to unsquish the gas. I have a little valve here where I can make sure that no other gas is leaving or entering the container. It's kind of like sealing the container off. Here it has a little pressure gauge, and right here it has a little digital thermometer. I can turn it on here, and you can see the temperature that it says. Right now, the temperature is at 22.2 degrees Celsius, which is the temperature of the room right now. Never mind, it's at 22.3 degrees Celsius. Now, here's what we do in an adiabatic process, is we start by applying work to the gas. I'm gonna apply that work now. Watch as I spin this thing like this. And you can see that as I spin it, what happens to that pressure, or what happens to that temperature? Temperature goes up. Now, spin it back the other way. Whoa. We can do it, we can do it. Spin it back the other way, and the temperature goes back down. What's happening here? Well, what's happening is that as I apply, actually I'll still show it to you. As I do work, as I push this thing down, I'm telling some little molecules, hey, get a move on. There's some little molecules that are in here. I mean, they're all moving around quite a bit, but there's some little molecules in here that are not moving that much. And then when I, whoa, color change. And then when I push down on this thing, I am literally shoving those molecules down. And I'm saying, molecules, get going. And they all start moving downwards. That's what happens in this situation. Color change back. So in an adiabatic process, what happens is you add in work, and that work becomes the thermal energy of those little particles because you're literally shoving them and making them move. Now, did you add in any heat? No, you didn't actually add in heat. That's not what you added. But when you added in work, oh, I need a pen. When you added in work, that work increased the kinetic energy of the particles by making them move faster, which in turn increases the temperature of the gas. Now, in this example, the temperature of the gas, for the most part, or the kinetic energy of the particles, for the most part, stays contained to that cylinder. So you don't let those little particles, they're not sharing their heat with their environment. They are just taking, or I should say their thermal energy. They're just taking that work, and now those particles are moving faster than they were before, and so because they're moving faster than they were before, they have more kinetic energy. So they do not exchange heat with their environment. They do not, the little particles do not give away heat. They keep it all to themselves, which gives you this temperature increase. If you were to write a delta U equation for this situation, you would say that delta U is equal to Q plus W. Now, first, we added in work. So we would say plus W here. And then the gas wasn't allowed to do anything with its heat except for keep it to itself. It wasn't giving it to its environment. It wasn't, I guess like taking it from its environment. No heat was being added. No heat was being taken away. So the amount of heat here is 0. That means that the internal energy of that gas is going to increase, and the amount that it's going to increase by is going to be equal to the amount of work that you put in. We can see this because the temperature of the whole gas goes up, meaning the kinetic energy of the particles goes up, meaning that now there's more thermal energy than there was before, so this thing did gain some internal energy. Notice you didn't put in heat, but you did end up with thermal energy. You put in work, and that work became thermal energy. So that's what you see there. Let's go ahead and look at a graph of an adiabatic process. Here, wait for it. Here's a graph of an adiabatic process. An adiabatic process. In this one, they actually have a gas that is expanding. Notice it starts at a smaller initial volume and it ends at a bigger initial volume. When it starts at a smaller initial volume and it ends at a bigger final volume, that means that the gas is doing work on its environment. So it's doing work on its environment, and that means it had to take away some of its own energy in order to do that work, so the temperature of it decreases. You can see the temperature goes down as the gas does work on its environment. Or the option that we looked at in class, or that we looked at, just now, said that we actually end with less volume and we start with more volume. This is squishing down. When you squish down, this whole curve goes backwards like this. So you start with a bigger volume, you end with a smaller volume, and what happens to your temperature? Well, here's your initial temperature, and here's your final temperature. Your temperature increases as you squish the gas because you squish the gas, so you add energy to it, and that energy increases the temperature. So that's an adiabatic process. The last type of process that we are going to take a look at today is a thermal process. And I'm going to write my delta U equation. An isothermal process, did I say thermal process? That's embarrassing. An isothermal process is a thermal process that occurs at the same temperature. An isothermal process is a process that occurs at the same temperature. The temperature does not change. Oh, geez, Louise. Oh, okay, well. Now I have to start over. Okay, fear not, fear not. Don't worry, luckily I have a great amount of resilience. Okay, hang on, make it red, Q. Then make it blue. blue. Okay, and back to our little kind of indigo-ish purple kind of situation here. Oh no, that was a really, really large box. Way far larger than I intended. Okay. No, don't do it. Don't do that. Don't end the recording. I'm sorry, this is literally such a pain. Okay, here we go. It's a thermal process that occurs at the same temperature. This is going to work the same way. I don't know why it keeps doing that. This is going to work the same way. Why? Hello? Please work, everybody. Everyone, just work. Okay. An adiabatic process and an isothermal process are very similar because they both start by adding work to the system. But in an isothermal process, you add work slowly. Take a look. I'm going to show you what happens here when we add work very slowly. Okay, make this nice and big. Scooch it back. Reorient ourselves. Here we go, here we go. Okay. Wow, sorry. Okay, once again, I'm going to do work on this gas. Let's crank it up a little bit. I'm going to add work to this gas, but this time I'm going to add this work very, very slowly and gradually. So you'll watch as I twist the little guy very slowly. Sorry, I got to get it reset really quick. Okay, so let's go ahead and close this off here. Turn on the thermometer. Can you see the thermometer? There. Okay, you can see that we're at 22.7. Wow, it's gotten warmer in here. We're at 22.7 degrees Celsius. And what I'm going to do now is I'm going to turn this slowly. Here we go. Oh, color change. Love a good color change. Hey, as I turn this slowly, notice what's happening to the temperature? Staying the same. It's still at 22.7 degrees Celsius. Now, what's happening here? I am doing work. I am absolutely doing work. So I am telling some particles that were sitting very still. I am telling them, hey, oh, look, we got a little temperature change. I am telling them, hey, you got to get a move on. You got to get moving. You're sitting there very nice and still. I'm going to need you to start moving. So I'm telling them to start moving, but I'm also giving them tons of time. Here's what happens. I tell them, hey guys, get a move on, and they start to move. But then I give them some time to run into the wall. They do start moving, but then they have some time to run into the walls of their container. And then they also have some time once they run into the walls of their container for the walls of their container that now has more kinetic energy to then exchange heat with the outside world. So the little molecules on the inside, which are moving very fast, they have time to transfer that heat to the walls of their container, which has time to transfer the heat to the environment. So as this little guy moves here, and I continue to move it very slowly, I think I started going the wrong way. Yes, I did. As I continue to move it, and I move it very slowly, I give it time to come to thermal equilibrium with its environment. In other words, I give it time to give its heat that it gains when it starts to get pushed down. I give it time to give that heat to its environment. That is what happens in an isothermal process. You do work, but you do work slowly so that the gas has time to give away its heat to its environment. Well, unless you go not slowly enough. Let's take a look here at what this would look like, or let's write it down. Move this out of the way, rearrange our lives. Okay, here we go. Here's what happens. You do work slowly. Oh, I need a pen. You do work slowly. This means that the temperature tries to increase as you make those kinetic, or as you increase the kinetic energy of the particles. But it has time to give that heat to the environment. Meaning it's going to lose heat. If we wrote this equation out as I seriously, guys, I don't know why it keeps doing that. If we wrote this equation out as a delta U statement, we would say that you put in work, but then the gas gives away heat, or the gas loses heat. This means that the total change in energy is 0 because you put work in and then the gas just released it back to the environment in the form of heat. That is an isothermic process. Let's take a look at a graph. Cursor mode, boop. Okay, here's a graph of an isothermic process. isothermic. Okay, here's a graph of an isothermic process. Do you see this one has the gas expanding? I like to show the gas decreasing in volume because that makes it a little bit easier, which flips the direction of the arrow here, but it's the same thing. Notice that over time, as this volume is decreasing, then the temperature is going to stay the same. You remember from last year, PV equals nRT. Well, hey, look, if you rearranged it and you rearrange it to say P equals nRT over V, but T is a constant, then you're going to have a graph that's basically a constant over V. In other words, you're going to have a P is directly proportional or inversely proportional to V kind of graph. Kind of like a Y equals 1 over X kind of graph. Does this look like a Y equals 1 over X kind of graph to you? For sure. You could also go the other way. If you go back the other way, then it will take heat from its environment in order for the gas to be able to do work on its environment. So it takes that heat in from the environment to do work, and you still have a net internal energy of 0 because the energy is just flowing through. It's either taking that work and giving heat to the environment, or it's taking that heat from the environment and using it to do work. And that is an isothermic process. Those are our 4 types of processes. And now for a little bit of trivia. Which 2 types of processes involve adding work? Isobaric and isovolumetric. Which 2 types of processes involve adding, oh, did I say adding work? Okay, let me reverse. Back up. Which 2 types of processes involve adding heat? You should say isobaric and isovolumetric involve you adding heat to the gas. Which 2 types of processes involve adding work? You should say adiabatic and isothermal. Those are the 2 where you add work. Which 2 types of processes end with a net internal energy or net change in the internal energy of 0, meaning the internal energy of the gas doesn't change because the energy flows in and flows back out again? You should say isobaric, heat flows in, work flows out, or isothermal, work flows in, heat flows out. Which 2 types of energy, or which 2 types of thermal processes actually change the internal energy of the substance? You should say isovolumetric and adiabatic. In isovolumetric, you add in heat and then you force it to keep that energy. It can't turn it into work. In adiabatic, you add in work and then you force it to keep that energy. It can't turn it into heat and give it to the environment. And those are the 4 thermal processes. Now for our last little diagram here. Okay, here's that question that we were talking about. We have a cylinder with a movable frictionless piston that contains an ideal gas that is initially in state 1 at blah, 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 blah. The gas is taken through a reversible thermodynamic cycle. When we say reversible thermodynamic cycle here, wait, pen, blue. Reversible thermodynamic cycle just means it starts and ends at the same place. So then you could do it over and over and over again, or you could do it backwards. Either way is fine. You would start and end at the same place. The questions that we're going to answer today are, let me get this guy out of the way here. Okay. First, calculate the net work done during the cycle, and then second was heat added to or removed from the gas during the cycle. Let's start with calculate the net work. Actually, before we do that, let's talk about what types of processes we have going on here. So we have a gas that starts here. When the gas starts here, it is going to start by going from point 1 to point 2 like this. Then after that, it's going to go from point 2 to point 3 like this. Then it's going to go, we'll go yellow, from point 3 back to point 1 like this. Wow, that is like really very aggressively yellow. Maybe we'll do something a little bit less aggressively yellow. Oh gosh, no, not that. Not that. Okay. Something like this. Okay. So now, first, when I look at this process here, I'm thinking this process here is probably an isobaric process. I'm saying it's probably an isobaric process because do you see that it happens at the same pressure the whole time? Then this guy looks like maybe some sort of combination of an adiabatic or an isothermal kind of process. And then right here, we have an isovolumetric process. Do you see that it happens at the same volume the whole time? Now, as for the total work done on the gas during the cycle, let's take a look here. If I wanted to know the total work done on the gas during the cycle, well, first, I could start by calculating the work done from part 1 to part 2. To calculate this work done here, I would find the area under the graph like this. Then it asked to calculate, then I would calculate the work done during the next part. So the next part I would do is the part from 2 to 3, and so I would calculate the work done in this section. Then the next amount that I would do is I would calculate the work done from 3 to 1, but hey, check it out. There's no area under that line, and we know that that makes sense because there's no work that's done during an isovolumetric process. So we say, that makes sense. Now, if we want to calculate the total work done, we would say that, let's find kind of a neutrally color here. Okay, I've been using blue for work, so we can use blue. We would say that the total work is equal to the work done in this first part from 1 to 2 plus, move my face out of the way, classic, plus the work done from 2 to 3. The purpley kind of stuff. Mine's a little bit bluer here, but it's the purpley kind of stuff. This. Sorry to trace over it again. I know that's obnoxious. Oh, but the colors are just so nice when they all match. Okay. Now, if I'm here trying to calculate the total work, the first thing that I'm going to do is I'm going to see what has positive work and what has negative work. Do you agree that here, I don't know why it keeps doing that or how I could improve to make it not do that. Okay, do you agree that here from 1 to 2, this amount of work, our volume is going from here to here, meaning my volume is expanding. If my volume is expanding, that's negative work. I am sorry, I don't know what to tell you. Then to go from 2 to 3, now look, my volume is actually decreasing from 2 to 3. So if my volume is decreasing, that means positive work energy is being added to the gas. So the total amount of work is going to be the work from 2 to 3 here minus the work from 1 to 2. Now, what I could do is I could calculate the work from 1 to 2. I could calculate the work from 2 to 3, and then I could take the work from 1 to 2 and subtract, or take the work from 2 to 3 and subtract the work from 1 to 2, or I could just do this. Like this. Because isn't the stuff that's left in the triangle, isn't that the work, the total work that gets done when you subtract the stuff on the bottom here, this work, from the total volume of this stuff on the top here? So I would say I could just find the total work much faster if I just do the area of a triangle. Again, if you could not do that, that'd be super awesome, but I get that the computer doesn't know what I'm doing. Okay, I can do 1/2 base times the height to find the total work done, where I'm just finding the area of that little triangle. The base here is going to be a change in volume, a delta V. The height here is going to be a change in pressure, a delta P. Well, then I could plug in a 1/2 and I could do a V final minus a V initial times a P final minus a P initial, like this. I could plug those numbers in based on the graph from here and here and here and here, and then I could get to a final answer. And that final answer would be the amount of work that gets done in total for this thermodynamic cycle. Okay, that's the first question. Hey, note that at the end, was it net positive work or net negative work? Well, total, it's going to end up being a positive number because do you see that there is more positive area than there is negative area, and so the positive stuff will win, which means that net over time this gas gained work. Now, was heat added to or removed from the gas during the cycle? You can say added, removed, or neither, and then justify your answer. Let's think about it for a second here. Here's how I go about answering this question. I say the gas started here. Again, why are we doing that? The gas started here at this volume, at this pressure. Then it experienced a isobaric process, then it experienced some sort of adiabatic or isothermal process, then it experienced an isovolumetric process, and it got back to where it started. If it got back to where it started, then the amount of energy that it ends with has to be equal to the amount of energy that it started with, or in other words, the total change in energy has to equal 0. There has to be a total of no change in internal energy because it's a reversible thermodynamic cycle, which means you could go this way and get to the same place, or go this way and get to the same place. You could do this again and again and again, over and over and over. So the amount of energy, since I start and end at the same place, oh gosh, that is not what I meant to do. Since I start and end at the same place, the amount of energy that I started with has to equal the amount of energy that I ended with, which means that there is a total delta U of 0. Now, that delta U, we know we can break down into Q and W. Well, hey, check it out. My Q is positive. It gained work over the whole time. So if work was done to this gas over the whole time, then heat would have to be removed in order to keep the total internal energy equal to 0. In other words, here I lose work, or here work or energy is taken out of the gas. Here that energy is added back into the gas. But now, in order to return to the same amount of energy as I had before, I'm going to have to take out a little bit of heat so that I can get back to the same amount of energy. And that's what we see here. You can tell that during this nice isovolumetric process. Do you see how I start with a higher pressure and I end with a lower pressure? That indicates to me that heat was taken out. So heat gets taken out in the end, and so I would say that heat is removed from the gas during this cycle in order to keep that total internal energy the same as where it started. And that's how we do one of those kinds of problems. And that is all for today, folks. Today we talked about the 4 types of thermal processes, which we see all of them are really just some sort of variation of delta U equals Q plus W. Sometimes we add in heat. Sometimes we add in work. Sometimes we add in heat and then we make that heat stay there. Sometimes we add in heat and we allow that heat to be released as work. Sometimes we add in work and then we make that energy stay there. Other times we add in work and we allow that work to be released as heat. And those are really all the different types of thermodynamic processes that you can go through for a little gas. And that is all for today, folks. I do hope that you have a wonderful rest of your day, and I'll see you guys next time. Bye, good people.